Hello and welcome to Math Zone African Motives. Today, we're diving into a powerful technique for solving systems of linear equations called Crammers' rule. By the end of this tutorial, you will be able to solve a system of 3 linear equations with 3 unknowns using Crammers' rule. Our main goal is to understand and apply Crammers' rule. This method relies on the concept of determinants, which are special numbers calculated from a square arrangement of numbers. It's a structured approach that can be very efficient, especially for systems with exactly one solution. Let's begin by introducing the tool we'll be using. In order to solve a system of 3 unknowns, let's call them x, y, and z, we must be given 3 separate equations that involve these variables. A crucial first step is to write all 3 equations in what we call standard form. This means arranging the terms so that the x terms, y terms, and z terms are vertically aligned on one side, and the constant terms are all on the right-hand side of the equal signs. The general standard form for a system of 3 linear equations is shown here. This structure is critical because it allows us to easily extract the coefficients to form determinants. Here, a1, a2, and a3 are the coefficients of x. Beyond b2 and b3 are the coefficients of y. Beyond c2 and c3 are the coefficients of z. And d1, d2, and d3 are the constants. Let's summarize the procedure for solving simultaneous equations for 3 unknowns using Crammers' rule. We'll follow a 6-step procedure. Step 1, as we just discussed, is to rearrange the equations into standard form. The variables x, y, and z must be lined up vertically, and the constants must be isolated on the right-hand side. So step 1, rearrange the equations into standard form. Step 2 involves finding the determinant of the coefficient matrix. We call this the determinant of the coefficients, or delta 0. In step 2, we find delta 0. To do this, we ignore the constants on the right-hand side and create a 3x3 determinant, using only the coefficients of x, y, and z. Then we evaluate this determinant. The next 3 steps are very similar. They involve finding 3 new determinants. Step 3 is to find the determinant of x, or delta x. For step 3, we find delta x. Here's the trick. We take our original coefficient determinant and replace the entire column of x coefficients with the column of constant terms from our standard form equations. Then we evaluate this new determinant. Step 4 is to find the determinant of y, or delta e. Similarly, we replace the column of y coefficients in the original determinant with the column of constants and evaluate. And step 5 is to find the determinant of z, or delta z. You guessed it. We replace the column of z coefficients with the constants and evaluate. We've now completed 5 steps. The 6th and final step is to apply Crammers' rule to find the values of our unknowns, x, y, and z. Step 6 is to apply Crammers' rule. Crammers' rule provides a simple formula for each variable. The value of x is found by taking delta x and dividing it by delta 0. The value of y is found by taking delta e and dividing it by delta 0. And the value of z is found by taking delta z and dividing it by delta 0. It's important to note that this method only works if delta 0 is not equal to 0. If delta 0 is 0, the system either has no solution or infinitely many solutions, and Crammers' rule cannot be used. Now, let's put this procedure into action with a step-by-step example. We'll follow it exactly. The question is, solve for x, y, and z using Crammers' rule. The system of equations is -5 minus 3i plus x equals -4z. The second equation is 1y plus 1z, minus 3 equals -2x. And the third equation is 4x minus 1 equals -3 minus 5s. As you can see, these equations are not in standard form. So our first task is to rearrange them. Step 1, standard form. Remember, we want x terms, y terms, and z terms on the left and constants on the right. Let's start with the first equation. -5 minus 3 plus x equals -4s. To get x, y, and z on the left, we'll add 4z to both sides and add 5 to both sides. This gives us x minus 3y plus 4z equals 5. Now for the second equation. Y plus z minus 3 equals -2x. We need to add 2x to both sides and 3 to both sides to get it into standard form. This results in 2x plus y plus z equals 3. Finally, the third equation, 4x minus 1 equals -3 minus 5s. Here we'll add 3 and 5z to both sides and add 1 to both sides. This gives us 4x plus 3 plus 5z equals 1. Now we have our system of equations in standard form. This completes our first step. We are now ready for step 2, finding the determinant of the coefficients delta 0. First, let's write down our system of equations from the previous step. Our system is x minus 3y plus 4z equals 5, 2x plus y plus z equals 3, and 4x plus 3y plus 5z equals 1. Delta 0 is formed by taking the coefficients of x, y, and z from this system. The problem states we should evaluate using row 1. To do this, we use the SEM principle, sign, element, minor. This requires the cofactor matrix sign pattern. The sign pattern for a 3 by 3 determinant is plus, minus, plus, then minus, plus, minus, and finally plus, minus, plus. We will use the signs from the first row, plus, minus, plus. So, delta 0 equals positive 1 times its minor, minus negative 3 times its minor, plus positive 4 times its minor. A minor is the determinant of the smaller matrix left over when you delete the row and column of the element you are using. Let's calculate these 2 by 2 determinants. The first is 1 times 5 minus 3 times 1, which is 5 minus 3, or 2. The second is negative 3, with the sign, which becomes plus 3. Its minor is 2 times 5 minus 4 times 1, which is 10 minus 4, or s. The third is positive 4. Its minor is 2 times 3 minus 4 times 1, which is 6 minus 4, or 2. Adding these up gives us 28. So, delta 0 is 28. Our result matches the provided solution. Now for step 3, finding the determinant of x or delta x. The process is the same, but the determinant we create is different. Remember, we replace the x coefficients in delta 0 with the constants from the right side of our standard form equations. We evaluate this determinant using row 1, applying the same SEM principle with the signs plus, minus, plus. Delta x equals positive 5 times its minor, minus negative 3 times its minor, plus positive 4 times its minor. Let's calculate the 2 by 2 determinants. The first minor gives us 1 times 5 minus 3 times 1, which is 5 minus 3, or 2. The second minor gives us 3 times 5 minus 1 times 1, which is 15 minus 1, or 14. The third minor gives us 3 times 3 minus 1 times 1, which is 9 minus 1, or it. Adding these products, we get 10 plus 42 plus 32, which totals 84. So delta x is 84. This also matches the solution provided. Now, let's proceed to step 4, finding the determinant of y or delta e. Following our rule, we will create this new determinant by taking the original determinant, delta 0, and replacing the column of y coefficients with the constants. The resulting determinant is 1, 5, 4, 2, 3, 1, 4, 1, 5. Once again, we will evaluate this 3 by 3 determinant using row 1 and the SEM principle. Delta E equals positive 1 times its minor, minus positive 5 times its minor, plus positive 4 times its minor. Let's calculate the values of these three 2 by 2 minors. The first minor is 3 times 5 minus 1 times 1, which is 15 minus 1, or 14. The second minor is 2 times 5 minus 4 times 1, which is 10 minus 4, or 6. The third minor is 2 times 1 minus 4 times 3, which is 2 minus 12, or negative 10. Now we perform the multiplication and subtraction. 14 minus 30 is negative 16, and negative 16 minus 40 is negative 56. So delta E is negative 56. This is consistent with the provided solution. We're making great progress. Let's move on to step 5, finding the determinant of z, or delta z. For this determinant, we will replace the column of z coefficients in our original delta 0 with the column of constant terms. This gives us the determinant. 1, negative 3, 5, 2, 1, 3, 4, 3, 1. As before, we'll expand along row 1 using the signs plus, minus, plus. Delta z equals positive 1 times its minor, minus negative 3 times its minor, plus positive 5 times its minor. Let's calculate the values for these three minors. The first minor is 1 times 1 minus 3 times 3, which is 1 minus 9, or negative 8. The second minor is 2 times 1 minus 4 times 3, which is 2 minus 12, or negative 10. The third minor is 2 times 3 minus 4 times 1, which is 6 minus 4, or 2. Now we calculate the total. Negative 8 minus 30 is negative 38, and negative 38 plus 10 is negative 28. So delta z is negative 28. This result also matches the provided solution. We've reached the final step, step 6, applying Crammers' rule to find our solutions. First, let's gather all the determinants we've calculated. We found that delta 0 is 28, delta x is 84, delta y is negative 56, and delta z is negative 28. Here are our 4 determinants. Note the important reminder from the problem. When we replaced the coefficients with the constants, the signs of those constants did not change. Now we use our formulas. To find x, we divide delta x by delta 0. So x equals 84 divided by 28, which is 3. The solution for x is 3. Next, to find y, we divide delta e by delta 0. This gives us y equals negative 56 divided by 28, which simplifies to negative 2. So y equals negative 2. Finally, to find z, we divide deltas by delta 0. We have z equals negative 28 divided by 28, which equals negative 1. Therefore, z is negative 1. And there you have it. The solution to our system of equations is x equals 3, y equals negative 2, and z equals negative 1. This matches the final answer in the solution. Let's recap what we've accomplished today. We have successfully solved a system of 3 linear equations using Crammers' rule. Here are the key steps again. We started by rearranging the equations into standard form. Then we calculated 4 determinants: the main coefficient determinant, delta 0, and 3 determinants for the variables x, y, and z by replacing their respective coefficient columns with the constants. Finally, we applied the simple Crammers' rule formulas to find our solutions. Thank you for watching this tutorial from Math Zone African Motives. If you found this helpful, please like this video and subscribe for more maths tutorials. Subscribe for more tutorials from Math Zone African Motives.